Hi everyone, this is Dr. G. Ravindranath Reddy, working as Assistant Professor of Mathematics, the Department of Humanities and Science in MLR Institute of Technology, Hyderabad. So we are discussing numerical methods and integral transform course. In that course, we are at vector differentiation. Now in this video, we will discuss what is a scalar point function, what is a vector differential operator, and by using this vector differential operator we are going to take the new concept, that is gradient of a scalar point function. So how to apply the gradient for the scalar point function? These are the points we are going to discuss in this video. So vector differential calculus is considered here, and it is extended to the basic concepts of differential calculus such as continuity and differentiability to the vector point functions. So in this we are going to learn a new concepts, that is gradient, divergent and curl. These are the three concepts we are going to discuss under this vector differential calculus. So now first we will go for the what is meant by a scalar point function. Suppose I have considered a three-dimensional space here. So for example, if you take a rod here and which is heated at one point. So now after some time the entire rod is heated. Now I want to take the temperature of this rod at this point P. So that is P of x comma y comma z. Now at this point I want to measure the temperature. So the temperature is represented with T at the point x comma y comma z. So since it is a heated rod, so at this point P, so we will get some temperature here. So when we consider this temperature is a scalar quantity, we know that the temperature is a scalar quantity. So this scalar quantity is existing at some point on that heated rod. And similarly, if you take all the points here, at each point you will get some temperature. So that temperature we can consider as the scalar quantity. So the scalar point function is nothing but the point at which some scalar is existing. That we can call it as a scalar point function. So for example, if you consider the definition here, consider the three-dimensional space. At each point P of x comma y comma z, suppose we associate it with unique real number called a scalar point scalar, which is represented with pi of x comma y comma z. So this pi of x comma y comma z we can call it as a scalar point function. So that is the example we have taken. Take a heated solid, take the point at P of x comma y comma z on that particular solid. So there you can get some temperature that is represented with the T of x comma y comma z. So this temperature we can call it as a scalar point function. That is the meaning of this scalar point function. And similarly we can take another example. Suppose a particle is tracing a path in the space. So when it occupies the position P of x comma y comma z, in that it will be having some speed. So speed we can consider as the scalar point function here. So when you come to this vector point function, same. So I will explain this definition here with some example. A particle is moving in the space at a point P and its path. A particle will have some velocity will be there at that particular point. So here we can consider this velocity is a vector point function. So similarly we can consider the acceleration of that particular point of that particle. So this acceleration is also a vector point function. So particle is moving. So suppose if the particle is at this point P of x comma y comma z, then at this point the particle will have some velocity. So velocity is nothing a scalar vector point function vector. So at this particular point we will we're having some a vector. So this vector we can call it as a vector point function. And similarly at this point if you want to find out the acceleration, so at this point the acceleration is will exist. So this acceleration is a vector function. So this we can call it as a vector point function at that particular point. So now we'll go for the vector differential operator. So the vector differential operator is represented with the symbol del and is defined as del is equivalent to I bar dou by dou x plus j bar dou by dou y plus k bar dou by dou z. So this is the representation of this del operator here. So once if you observe this del operator, so only with this, if you take this only operator del, it does not have any meaning here. So if you want to get some meaning for this del operator, you have to operate this on the either on scalar point function or vector point function, either pi or del f bar. So then if you operate this operator on some scalar point function or vector point function, then it will have a meaning here. So only for this del, we don't have any meaning here. So if you operate this operator on some scalar point function or vector point function, then it will have a meaning here. So the operator possesses the properties of ordinary vectors as well as the differentiation vectors. So now by using this operator, del operator, we are going to define a new concepts, that is gradient and the divergence and the curl involving this operator. So by using this operator, these are the three new concepts we will get in the vector differentiation, that is gradient, divergence and curl. So now just now you have seen this operator has no meaning itself unless it operates as some suitable functions here. So already we said that we don't have any meaning for this operator. So if you want to get the meaning for this operator, we have to operate this operator on some functions, either it may be a scalar point function or it may be a vector point function. Then only we will get the meaning for that operator. So this is about the vector differential operator, so which is defined by I bar dou by dou x plus j bar dou by dou y plus k bar dou by dou z. Now one by one we will first you concentrate on the gradient. So what is the use of this gradient? How can you find out that gradient on that scalar point function? And this we will discuss in this video here. So now gradient of a scalar point function. So I have given you a scalar point function pi of x comma y comma z and asked to reduce this scalar point function into a vector point function as f bar. So whenever we want to reduce any scalar point function to a vector point function, then we can apply the concept of this gradient. So now we'll see how to find out how to convert this scalar point function by taking help of this gradient concept. So I have taken the scalar point function pi of x comma y comma z. Be a scalar point function on some region on the space. Then the function I bar dou pi by dou x plus dou pi by dou plus j bar into dou pi by dou y plus k bar into dou pi by dou z is known as the gradient of that scalar point function. It is denoted by del pi. Now we'll see how we got this value here. So del pi represents the gradient of that scalar point function. So del is a differential operator and pi is a scalar point function which we have taken. So that scalar point function we can represent with pi. And now whenever we want to find out the gradient of that scalar point function, that is represented with the del pi. So now del, we know that differential operator, it is represented with I bar dou by dou x plus j bar dou by dou y plus k bar dou by dou z into this scalar point function. Now you send this, you remove these brackets by multiplying with each term with this pi scalar point function, you will get I bar dou pi by dou x plus j bar dou pi by dou y plus k bar dou pi by dou z. So once if you get this value, if you get this dou pi by dou x value, dou pi by dou y, dou pi by dou z, if you replace that values, partial derivatives values in this, then this scalar point function will be converted into a vector point function. So now this is about the gradient of a scalar point function. Now we will take some scalar point functions and we will see how to find out this gradient for that scalar point function. So we have some basic formulas are there. So suppose I have given a scalar point function which is a surface. So now if you want to find out the unit normal vector to that given surface, it is given by del f by modulus of del f. So modulus of particular vector is nothing but the magnitude of that vector, which is defined as, suppose f1 f is equal to f1x f1 I bar plus f2 z bar plus f2 k bar f3 k bar. So then modulus of f bar is equal to, we can take it as square root of f1 square plus f2 square plus f3 square. This is the way how we can find out this gradient of this magnitude of this vector point function. So now similarly, if you want to find out the normals to the surface, angle between the normals to the surface is, we have the standard formula that is given by cos theta is equal to m1 bar. This is one normal vector to the given surface, and n2 bar is the normal vector to the given surface. So now this formula is used to find out the unit normal vectors. Now whenever we want to find out the normal vector for the given surface, then it is enough to find out that gradient value for this scalar point function. Okay. So now by using this formula, we are going to find out the angle between the normals to the surfaces here. Now this is very important. Then the directional derivative of a scalar point function phi at the point p of x comma y comma z in the direction of unit vector is given by e bar dot gradient of pi. So by using this formula, we are going to find out the directional derivative for the scalar point function at a given particular point in the direction to the given vector. Okay, so whenever we want to find out the directional derivative, we want a scalar point function, and where the particular point where we want to find out the directional derivative, that is a point we need. And now we have to consider the direction in which we have to find out the directional derivative. So that directional unit vector. So this unit vector represents the direction here. So based on these three, we are going to find out the directional derivative for the given scalar point function. So next, unit vector. This is unit normal vector. This is only normal vector here. So the normal vector for the given surface f is given by only del f, that is gradient of f. So these are the important formulas we have to remember, which comes under the gradient of a scalar point function. Now by using these formulas, we will see how to find out the unit normal vector, how to find out the angle between the normals to the surfaces. So and the important concept is how to find out the directional derivatives of the given scalar point function at the given particular point. So now we will take one by one here problems. Now first we will take the unit normal vector to the given surface x square y plus 2xz is equal to 4, and this is the surface he has given, and on this surface at this particular point we have to find out the unit normal vector. So we have the standard formula to find out that unit normal vectors. This is our standard formula here. So this is our standard formula to find out the unit normal vector to the given surface. Now use this formula. So first we have to reduce that given surfaces. So whenever we are having some equality equal to some RHS exist, so you bring this constant to this, and enter x square y plus 2xz is equal to 4. You bring this constant term to this side, it becomes x square y plus 2xz minus 4 is equal to 0. So you consider this as the scalar point function, which is represented with f. Or if you want, you can take pi also. We don't have any problem here. Okay. So now this is our scalar point function given in the problem. Now we have to find out the del f value here. So what is our del f? Del f is Del is a operator that is which is represented with I bar dou by dou x plus j bar dou by dou y plus k bar dou by dou z into f. So if you send this f scalar point function to this side, it becomes I bar dou by dou x plus j bar dou f by dou y plus k bar dou f by dou z. So now if you know these partial derivatives of the scalar point function with respect to x, with respect to y, and with respect to z, if you get these three partial derivatives, then within seconds we can find out our normal vector here. So for this one, what I want to do is I want to apply the differentiating with respect to x, y, z partially. So once if you apply the partial derivative, so we know how to apply the partial derivative here. Dou f by dou x is equal to dou by dou x of f. What is our scalar point function? This is x square y plus 2xz minus 4. This is our scalar point function. So now that means here we are having in three variables here x, y, z, but we are applying the partial derivative with respect to x. So whenever we are applying the partial derivative with respect to x, we have to consider the remaining two variables y and z as constant. We should not forget this. So now dou by dou x of first term. What is our first term here? X square y plus dou by dou x of 2xz minus dou by dou x of that constant 4. So this is equal to, so since we are applying the partial derivative with respect to x, so we have to consider y as constant, so keep that y as it is, take that y outside this partial derivative, and the remaining one is only x square will be there. So derivative of x square we can take 2x plus, similarly 2 is constant, so we can take 2 outside, and since we are applying the partial derivative with respect to x, we have to consider z as constant, so take that z outside. The remaining one is only x. Derivative of x with respect to x is 1 minus, and 4 is a constant, whatever it may be, either it may be a partial derivative or ordinary derivative. Whenever we want to find out the derivative of that constant, then that is always equal to 0. Derivative of constant is 0. So now you will get this value is equal to 2xy plus 2z. So this is the value we have taken, and similarly follow the same thing for partial derivative of f with respect to y, you will get only x square, and partial derivative of f with respect to z, you will get 2x. So these are the three partial derivatives of f with respect to x, y, z. So now we are ready to go for this del f value here. So this del f, already we have seen del is a differential operator which is represented with this I bar dou by dou x plus j bar dou by dou y plus k bar dou by dou z into f. Send this f inside, it becomes I bar dou f by dou x plus dou f by dou y plus dou f by dou z. Now already we got these values here, so replace that values here. So dou f by dou x we got. So in place of dou f by dou x, we can take 2xy plus y, 2xy plus 2z, and in place of dou f by dou y, we can replace with y x square, and in place of dou f by dou z, we got that value is equal to 2x. So this is the value of del f. So now we have to find out this at that particular point. He has given the point. Suppose if the point is not given, then we can take that vector as that gradient of that scalar point function as this one. So whenever he has given a point, particular point in the problem, then we have to find out this del f value at this particular point. So now you substitute that particular point here. So what is our point here? 2 comma minus 2 comma 3. So since we are discussing in the three dimensional, so we can represent that ordinates as x comma y comma z. So you consider this value as x, consider this value as y, consider this value for z. So now wherever we are having x, replace x with 2, and where y value with minus 2, and z is equal to 3. So if you replace this, you will get our required vector at this particular point. Now here in our problem we want unit normal vector, that is given by del f by modulus of del f. So now we got this del f value at that particular point. Now you apply the modulus of del f here. So we know how to find out the modulus of del f. Go to the del f at that particular point. So is equal to square root of I bar coefficient, that is minus 2 whole square, plus j bar coefficient 4 square, plus k bar coefficient 4 apply square. So you will get square root of 4 plus 16 plus 16. So this is equal to square root of 32 plus 36, which is equal to 6. So here, hence, the unit normal vector is given by this. So if you want, you can take common, 2 common, and we can simplify this. So here, now apply the same thing. We in the denominator we got a del modulus of del f equal to 6. Take the 2 common from the numerator. 2, 3 gets cancelled, 2 and 6 gets cancelled. You will get this remaining minus I bar plus 2j bar plus 2k bar by 3. This is our required normal vector, unit normal vector. So if you want to find out only normal vector, then we can stop our problem at this point. Del f, suppose if the given point is this one, we can stop at this. So but in the problem is asked to find out the unit normal vector. So now we have to use this standard formula and then substitute the values of del f and the modulus of del f. You will get our unit normal vector for that particular surface at that particular point. Now we will take the another problem, how to find out the angle between the normals to the surface. This is the surface he has given, and now on this surface, this is one point and this is another point, and these 2 points we have to find out the normals. And now whatever the angle makes by these 2 normals on that particular surface, we have to find out that angle here. That is the meaning. So as usual, you consider that a scalar. So this is our surface we have to consider as a scalar. So it is given by xy is equal to z square. Now bring this z square to this side. It becomes xy minus z square is equal to 0. You consider this one as our scalar point function. So that's why we have taken f of x comma y comma z is equal to xy minus z square. Now since he has given 2 points here on that particular surface, so at this point on this surface, you consider n1 bar as the one normal vector, and at the second point on the same surface, you consider that second normal as n2 bar. So since he has given 2 points on that same surface, so you consider that at one point whatever the normal vector you get, you consider that normal vector as n1 bar, and the second point where whatever you get the normal vector, you consider or represent that normal vector as n2 bar. So how can you find out that normal vectors? We have the formula del f. Follow the same procedure. So you will get this del f, and now take the point. So at this particular point, you find out that whatever the vector we get, that vector is represented with n1 bar. And similarly, take the second point and substitute in the same del f value, you will get another vector. You consider that as n2 bar. So whenever he has given a single surface, and that single surface, if you have given two points, then at these 2 points you find out these normal vectors on that particular surface. So now use the formula. Let theta be the angle between the normals. We have the formula. Substitute that n1 bar in place of n1 bar dot. We should not forget this dot. This dot is very important in the vectors. So n2 bar by its magnitude. So in the numerator we are having a dot product in between these 2 vectors. We know how to find out the dot product here. So how to find out this dot product here? So in the first vector, take the I bar coefficient, and in the second vector, take the I bar coefficient and then multiply these 2. So you will get I bar coefficient is 1 and j bar I bar coefficient in the second vector is 3. So 1 into 3, 3. And here we are having plus, and here also we are having plus. So plus into plus, plus. Now go for the j bar coefficient from these 2 vectors. J bar coefficient is 4 in the first vector and j bar coefficient is 3 in the second vector. So now you multiply these 2. 4 into 3, that is 12. And here minus, and here we are having plus. So minus into plus minus 6 into 4, 24. by this value here. So you will get this value is equal to minus 9 by root 33 into root 54. Now if you want theta value, so send this cos to this side, it becomes cos inverse of minus 9 by root 33 into root 54. So this is the way how we can find out the angle between the normals to the surface. So next, so in the previous problem he has given a single surface with 2 points. Now in this problem he has given two surfaces with single point. So once if you observe the difference between the previous problem and this problem is, he has given only one vector point scalar point function with 2 points, but in this problem he has given two surfaces, one is f1 and f2, and given only 1 point here. So that is the difference between the previous problem and this problem here. So whenever we has given two surfaces, you represent that surfaces as one as f and another one as z, your wish. You can consider f1 or f2 or f or z. So these are the two surfaces he has given. First what we have to do is, for this surface you find out the normal vector, and for this surface also you find out the normal vector here. So you will get that normal vector is del f, here the normal vector is del z. So now we know how to find out del f and del z. Follow the same procedure here. You will get del f value and del z value here. Now after finding the normals for these two surfaces, we have to take the point into the consideration. At that point we have to find out the normals here. So the angle between the surfaces he has given n1 bar. Whatever the first vector we get, you represent that vector at that particular point, and del z you take that whatever the normal we get for that second surface, you represent that as n2 bar and take the point here. Follow the same procedure. You substitute that n1 bar and the n2 bar, apply the dot product in the numerator, you will get our cos theta value. Send that theta to this side, it becomes cos inverse of square root of 19 by 29. So once if you identify the difference between the previous and this problem here, that is very important. Now this concept is very important, that is how to find out the directional derivatives for the given point, given scalar point function, the particular direction of vector with that particular point. So whatever the scalar point function he has given, you take that scalar point function, find out the normal. So our directional derivative formula is E bar, that is the vector he has given, vector we are considering in which direction we have to find out that directional derivative, that is represented with E bar, and apply the dot product. And now take the scalar point function and find out the normal, this one you will get del f, and this take the point 1 comma 2 comma 0, apply the dot product, we get our required directional derivative of that scalar point function in that particular direction of this vector at this particular point. So f is equal to this del f at the particular point. This is our del f value at that 1 comma 2 comma 0. You got this value here. Now E bar is a unit normal vector. So E bar represents the unit normal vector of this given vector. So we know how to find out the unit normal vector, that is vector by its magnitude. I bar plus 2j bar, this is the vector and this is our magnitude of that vector. You find out this. So you will get our E bar value here. Now you substitute that E bar value on del f value at this particular point. So E bar dot del f is equal to, that is 1 by 3. We know how to find out the dot product of these two vectors. So multiply corresponding coefficients of phi bar, j bar, k bars and add them and divide with 1 by 3, you will get 10 by 3. So 10 by 3 is the directional derivative of this scalar point function in the direction of this vector at that particular point. Okay, so we have different models are there in the directional derivatives. Now we will discuss that models here one by one. So the basic model is, In the problem, you will give the scalar point function. Each and every problem, you will give the scalar point function and the point where we have to find out the directional derivative, and the difference you can find the difference only in the vector. In the direction of here we have to get the vector, but some problems they will give that directly the direct vector. In some problems we will not give the vector directly here. First we have to find out that vector, then we have to go for this standard formula. So now let us take the another model here. So find the directional derivative of. So this is the scalar point function he has given. This is the point he has given, but in the direction of normal to the surface. So in the previous problem directly he has given that vector point function, but in place of vector point function he has given the normal to the surface at this point. So now you take this surface, you find out the normal n1 bar at this particular point. So then you consider this n1 bar as the our required vector f bar. You find out that e bar value by using this f bar value. So this is the changes you can find in the directional derivatives in the different models. So first you take g of x comma y comma z. So this is the surface he has given. I will consider that surface as with z. So 3x square, 3xy square plus y. You bring this z to this side, it becomes minus z. You find out del z value here. We know how to find out that del d. This is the value we get. Now take the point where we have to find out the normal to the surface. You substitute that point, you will get our vector point function. So you consider, since it is a normal, so we will represent that normal vector as n bar. So now by using this vector, we have to get the e bar value here. What is our e bar? N bar by its magnitude. Okay, so this is e bar is equal to n bar by its magnitude. So you will get this value here. So now in place of this we got this e bar value. This part is completed. Now you concentrate on this part. That is, if this is a scalar point function, now we got a e bar value. In the formula we are having e bar dot del f. Now the second part is whatever the given scalar point function is given, for this we have to find out the gradient value here. So find out that gradient, this consider that one. It's so del f is the gradient. So this is the value we get. Now you take the point 1 comma 1 comma 1. This is our del f at that particular point. Now this is the formula e bar, we got that e bar value. Del f at this particular point we got this vector. So now you multiply these two vectors, dot product, you will get our required directional derivative. So this is another model in the directional derivative. So once if you observe this problem and the previous problem, in the previous problem he has given the vector directly in the problem itself, but here in the second problem, instead of giving that vector directly, he has given normal to the surface. Just now we have seen how to find out the normal to the surface at the particular point. So whatever the normal vector we get, we have to consider that normal vector as f bar, and by using this f bar we have to get the value of e bar. Okay, that is the difference between this problem and the previous problem here. So now like this we are having different models in the directional derivatives, so we can practice that. Now in this video we have seen how to apply the gradient for the scalar point function, and different models we have seen on the gradient of a scalar point function. Now in the next video we are going to discuss what is the use of divergence of a vector point function. So how to find out the divergence of a vector point function. All these things we will discuss in the next video. Thank you.